Well, good afternoon. I'm John Sengenberger. I lead the alumni relations team here at the Tepper School of Business at Carnegie Mellon University. And we are delighted to have you join us this afternoon for our Tepper faculty webinar on artificial intelligence. I think it'll be an interesting and stimulating discussion today with Professor Zach Lipton. So glad to have you with us in our virtual classroom. We've had commencement here at the university. We've had our alumni reunion weekend, so things are getting a bit back to normal, but we still want to provide you with this opportunity to join us from wherever you are for our virtual classroom, to hear from our outstanding professors on the work that they're doing, the research that's going on here at the university, and the amazing things that are happening as part of the intelligent future at the Tepper School of Business. So first, before we begin, let me make a few announcements. First of all, we are so happy to be able to be doing in-person events again. I was delighted to be able to be out and hold receptions in Seattle and Boulder and Denver, Colorado, in Palo Alto and Chicago and Los Angeles in the last week or two. And we have upcoming receptions, one tonight this evening in Pittsburgh. We've got one in New York City next week, as well as one in Boston. And we're looking forward to our annual summer event at O'Brien Vineyards, Bryan Estate Vineyards in Napa in July. So if you're interested in attending or have an interest in that, just email us at tepper-alumni and we'll get you some information on that. So thank you so much for joining us. It's also, we're getting close to June 30th. When I ask alumni what's June 30th, and that's the end of our fiscal year. It's the time when we ask all of our alumni, if you've not yet made your donation to the Tepper School or to Carnegie Mellon University to help support the mission, the academic mission of the university and the school and our students, we would ask you to please make your gift by June 30th. You can just click on that link there, it's tepper.cmu.edu/give, and choose where you want to give to the school. There's many opportunities to support our students, our faculty, our programs here at the school, but we really need everyone's participation to help make that successful. So thank you to those of you who've already given to us, and to those who are going to give in the next couple of weeks. We appreciate it very much. You are really our stakeholders. You're part of our mission, and we appreciate having you with us and having your support. Now let me introduce our faculty speaker today. Professor Zach Lipton joins us from his undergraduate degree in math and economics from Columbia University. He got his MS and his PhD from the University of California in San Diego's Artificial Intelligence Group. He came into his career as a professional jazz musician and then transferred his zeal and his intellect into machine learning and operations research, where he currently is appointed here in the School of Machine Learning department at the School of Computer Science. He also teaches at the Tepper School of Business, and he also holds positions at the Heinz School for Public Policy and Societal Computing. So he's a very busy man and got a lot of interest across campus. He also directs the Approximate Correct Machine Intelligence Lab at Carnegie Mellon University, where he'll talk about leading his team of PhD students in their work. Zach comes to us with research interests in machine learning, healthcare, technology, society, natural language processing, and robustness and causality. He'll be talking all about those things today, and we're really happy to have him back with us on our webinar series. So join me in welcoming Professor Zach Lipton. Zach?
Hey, thanks so much for the warm introduction, John. Nice to meet you, everybody. I'm just going to share my screen here. Ultimately, where we want to get in this talk is talking about building more robust and adaptive systems that we can sort of trust in dynamic environments and use to guide decision-making. But to start, I'll probably do just I will definitely do. So some amount of kind of level setting of just some sort of context for those of you who are coming from a more general background and not necessarily a career in AI research. So I'll talk a little bit about my group and also set up a little bit of just the broader landscape of where this technology is and what its capabilities are and what some of the exciting developments are that's like why are we even talking about AI in the first place before we start talking about some of these sort of critical concerns and sort of shortcomings of the existing generation of technology and the research we're doing to improve it. So like John said, I lead a group. This is just sort of like our current crop of PhD students, although I guess it's I need to cross one off because Ricardo, who is in the center on the first row, did a great job defending his dissertation on Monday. So he is, unfortunately for us, that means, he will go off and do great work in some other environment now. And, we won't have him next year. It's a fairly diverse group of students in many ways. But besides the sort of difference of experience and expertise that they sort of bring coming into lab, a diversity of focuses academically. So I want to kind of situate the breadth of the work they do and sort of what are the like cross-cutting themes that really make the lab cohesive. Because, we have some students who are kind of more like mathematical powerhouses who come here as sort of theoreticians and people who do work more on the theoretical foundations and statistical foundations of machine learning side. We have some students who do work that is really deeply engaged with has a more salient feature that's kind of more humanistic, concerned with the effects of technology on social systems and the integration of technology into human decision making. And we have some folks who focus on some key application areas that we are focused on. And these include natural language processing and in particular applications in healthcare where even across modalities, computer vision, natural language processing, electronic health record data. So what's the sort of like broader concern? Why do we call the lab the approximately correct machine intelligence lab? It's kind of a pun. On one hand, when you learn about machine learning in a kind of formal way, the sort of dominant way of talking about the sorts of formal statements you could make about machine learning systems is usually that they are probably approximately correct. And that might sound like a mouthful, but what it's saying is just that, unlike when you do pure math or when you develop traditional algorithms, you say something about it's either correct or it's not correct, and you just prove that it's correct. In the context of machine learning, you're learning from data and you're trying to generalize to data you've never seen before. And whenever you have problems with a sort of statistical character, there's a sense in which the best you could be is, with high probability, very close to the right answer. It means like most of the time you get an answer that's very close to the correct. And this is true even for the most simple problems, right? If you wanted to say, what is the average height in the population? You could never tell me without actually touching every single person in the population. What you could do though is you could sample from them. You can get out a representative sample. You could measure everybody's heights. You could take the average of the sample and you could do some statistical analysis to say, okay, if I make some mild assumptions, like nobody is more than 100 feet tall, then I could say, okay, based on the sample that I have and that, that sample's a random sample, here's my estimate of, the average height in the population. Here's a confidence interval. I'm confident that it lies in. So that's probably approximately, I'm pretty confident that it's within a close distance of this estimate. So that's one sense in which all machine learning is in some sense or another. It's not always as straightforward as a confidence interval and a mean estimate, but some sense in which our systems are always sort of at best, probably approximately correct. But we use the term in a more loose and more kind of, maybe like more like broad, in a broader sense, it's like maybe like a more, I don't know, I'm tempted to say a more profound sense in which this technology is approximately correct, which is that if you look at what's going on in AI right now, and you look at what's going on in machine learning, we're coming up with systems where we have, not just that we have a, approximately correct solution to the problem we set out to solve in a sort of formal way, but the problem formulation itself is usually kind of a crude, sandbox, like toy approximation of what we really want to do in the real world. Right? What we really want to do in the real world is make better treatment decisions for patients. What's the machine learning problem we come up with? It's something like, predict a diagnosis, predict the length of stay, and then how does this actually relate to making better decisions? Even if we can solve this task pretty well, how do we operationalize that? Is it actually overall improving healthcare? Hard to say. We're working on this, what we call like a surrogate problem, right? We come up with we round off all the corners to come up with a problem that is sort of fits with a sort of machinery that we have. And this is true in all kinds of contexts. It's true when we deploy these systems in criminal justice. What do people do? What you like to do is make more just decisions about who gets bail and who doesn't, and at the same time, sort of, be responsible in terms of public safety. But what do we actually do? People do something like look at a bunch of features, predict likelihood of arrest. There's a bunch of things that are important in the real world that are missing from that. You don't have the machine learning doesn't know about concepts like procedural justice. It doesn't know about notions of what is relevant and what is not relevant, not in a statistical sense, but in a like causal sense. So we're always doing this kind of dance of simplifying problems, of failing to model some important aspects of the real world that really matter in human decision making. And so when we come up with a machine learning system, someone says it's accurate, there's sort of two issues. One is sort of how accurate, but the other side is accurate at what? And the answer is usually something like for solving a very specific problem that is not capturing everything you actually care about. And even then, doing it under some kind of idealized assumptions. And where we push as a lab is, I think, there's a few different ways you make progress in machine learning research. And one of them is you sort of take the problem formulation for granted and you come up with better methods. You say, okay, I accept that my goal is just, given this data, predict this target. I want to come up with better methods, either in a sense that I can theoretically guarantee that the method will be better under certain conditions, or experimentally come up with methods that are like in practice doing better at this very narrowly defined problem. A different way that you make progress is you look at what we're doing in machine learning and you look at what we care about in the real world and you think about, how do I actually enrich the space of problem formulations that we work in? How do I actually come up with new problem formulations that are capturing some aspect of the real world that we care about, but was maybe previously not modeled, not incorporated into the way we think about developing AI systems. So that I think overall tends to be our impulse. And for that reason, that's like the real reason, I think, the sense in which our lab is, concerned with like the approximately correct nature of ML. It's really in the space of the problems we're addressing. And so this sort of broader research agenda, on one hand, it concerns how do we build systems that are robust under various models of how the world might change. Most ML is developed under the assumption that the world is just sort of static. And that's something I'll talk about mostly today. But I also want to stress that we're also very interested in, most of the time people are training predictive models. And what we actually care about when you look closely in many of these situations is actually guiding better decisions. When people talk about, say, personalized medicine. Well, to have personalized medicine, it's not enough to be able to make personalized predictions that incorporate, contextual factors, something about someone's specific health record to say, how likely are they to die? To make a better decision, you have to say, how much less likely would they be to die if we gave them this drug, which maybe otherwise they wouldn't have been given. We want to be able to do this kind of counterfactual reasoning. What would be the benefit? When you start saying what if, or what would be the benefit if we did something different? These questions all have the flavor of a causal inference problem. And broadly, we are getting more and more interested in doing more work in the space of causal inference and discovery. And another area where we have a lot of issues that are salient in the real world, but missing from a lot of ML formulations is concerns of a more like ethical nature, moral character of what, when you have a system that's being used to guide decisions in healthcare and allocating scarce resources and criminal justice, what are the various sort of, moral and political concerns that we have as a society that are not being captured in the ML models? And what's the right way to operationalize, various concepts of, say equity or justice into the way we develop this technology? So that's sort of on the conceptual side we work on. And on the application side, we're very concerned with problems in healthcare. We especially tend to look from a modality standpoint at natural language, but we're not, we also look at a lot of other things like electronic health record data, computer vision. And, we do a lot of collaborations with sort of institutional decision makers. So Ricardo, my student who just graduated, for example, does a lot of work with criminal justice. And in that case, he's looking at the various sorts of instruments people use to guide decisions that are, in areas like pretrial detention or bail decisions or sentencing decisions. So these are all kind of broadly, the kind of focuses of my lab. So now you know something about who I am and what we care about. And I'll, happy to answer any questions about any of those things as we go on. So now back to like basics, square one. What is machine learning? What are we talking about? So when we say AI these days, there's a long, complicated history that, could easily take hours. And we kind of delved really deep into it. I taught a course last semester on the philosophical foundations of machine intelligence. And one part of that was really examining machine learning and broadly the broader set of programs associated with the pursuit of machine intelligence as disciplines. And, who are these people? What are their commitments? What are their problems? Or who are we? And, that's a long, complicated story. There was a movement something called cybernetics, which was concerned with that's where a lot of our current techniques came out of, ideas like around control theory and reinforcement learning and neural networks actually came from cybernetics. There was another field called artificial intelligence that sprung up that was more focused on logic-based systems and trying to program rules and knowledge. And that's mostly not what almost anyone is talking about when they say artificial intelligence today. But the people who called themselves artificial intelligence, who coined that term at the time, there were other things that they did that do have a legacy in what we're doing today. Like the sets of problems that they carved out as, their challenges included natural language processing, machine translation, computer vision. So a lot of their key challenges are still a lot of the key areas of machine learning today. But we're using methods that look more like cybernetics. So this is a long, complicated history that, we could get lost in for hours. But at the end of the day, one thing to know is that maybe a lot of these terms have morphed over time. What we call artificial intelligence today has methodologically very little to do with what the term originally meant, although there's some shared, commitments about what sorts of problems we're working on. Today, when you hear the term AI used, it's almost always referring to machine learning methods. So the term AI broadly doesn't have any commitments about what are its methods. When people use the word AI, it's sort of an umbrella for intelligence systems, machines that do things that we thought required intelligence or we thought required human intelligence until recently. Machine learning is specifically that family of methods, approaches to these sorts of problems, where the idea is that we don't know how to program. With AI, you have some things that have been called AI, where you're going to go talk to the experts and figure out what they know and try to codify it as a computer program. Machine learning doesn't work like that. There's some role for expert knowledge, but at the end of the day, the assumption, the working assumption is that we don't know how to just sit in a room with the experts and write down the computer program. So instead, what we're going to do is instead of programming, the model that performs the task we care about directly, we're going to go out there and we're going to get data, or we're going to create an environment that an algorithm can interact with. And instead of coding the exact program we want directly, we're going to develop a kind of very flexible program whose behavior is modulated by, a large number of knobs. We call them parameters. You might have 1 billion parameters or 1 trillion parameters in your model. And the idea is that our system is going to interact with some kind of environment. This could be truly interactive, or it could just be in the form of passive data acquisition. And the idea is that the model should get better and better and better the more experience it has, where experience sort of just means more interaction, or in the passive case, just more data. So you take the translation system that powers Google Translate now. If you just had one book where you had, let's go even more extreme. You just had one sentence in English and the corresponding translation in French, and you train a system, you get a really terrible machine translation system. But if you went and got 1,000 sentences in English, and each one you have the corresponding sentence in French, you train the system, you get something that is still pretty terrible, but not as terrible as the one that only saw one sentence. You go out and get, just turn the knob all the way, you go out and get all the books that have ever been written and translated into French, and you align them sentence for sentence, and you feed each pair of sentences into the system, and the system turns all the knobs to try to make it so that it's likely to output something like the ground truth translation when confronted with the, when they put in the English sentence, it gives high probability to the corresponding French translation. You find that these systems start performing really, really well, and not just on the data you've given it to already, but they generalize to unseen data that it's never seen before. Now, obviously, if you give it to something truly out of left field, the system will break. But if you give it something that is, something you plausibly could have seen in the data set, even if you've never seen that exact sentence, it's statistically something that, could have been there in the data set. These systems actually are strikingly impressive right now. And so machine learning is this family of technology. And if you go out there and you use Google Translate, you use speech recognition to dictate your text messages, your iPhone turns on and looks at your face and knows who you are and unlocks. Any of this stuff, this is all technology that was trained in this fashion by looking at many, many, many examples, extracting a pattern that now generalizes to new instances. The dominant approach for building these systems is a class, inside the machine learning system, you need some kind of form of a model that takes your input and maps it to the output. And those models can take many different forms. The dominant form of a model now is something called a neural network. It's important not to overstate the biological nature of these systems. People see neural network and they say, oh, it's a machine brain. It's not a brain. It's not conscious. It's not sentient. It's a cartoon of a brain, but it draws a few important intuitions. It's not even a cartoon of a brain. It's just a kind of model built from a cartoon of a neuron. And the idea, the key insight is that the brain is a very complicated organ that we don't even begin to really understand. Even now, even with decades of groundbreaking work in neuroscience, we still have no idea how the brain works. We're in the infancy of understanding how the brain works. But what we do know is that the brain does really complicated things, despite the fact that it's made up of billions of neurons, each of which is comparatively simple. There's no neuron that by itself thinks. There's no neuron that by itself recognizes complex objects. This doesn't exist. And yet, when you compose together many, many, many neurons, each of which receive signals and then output signals to other neurons in this kind of cascade sort of behavior, you're actually able to build a very, very, very complicated system out of very simple components. Think like an ant colony could do all kinds of things that a single ant can't. Or each of us there's no person who knows how to build a computer, and yet collectively, maybe I don't know, maybe there's one crazy person out there, but I doubt it. But somehow collectively, we're able to organize into communities that are capable of building computers from raw materials in the world all the way up to complicated software. And so neural networks are these models. They're very complicated models built from very, very, very simple cartoons of neurons. And the way it works is you feed in your data. Basically, the data are the values taken by the first layer of neurons, these little orange circles here. And then you compute the value of a bunch of what we call hidden layers of neurons, where each hidden layer in turn sort of influences the next hidden layer all the way until you get to your output. And initially we have no idea what is the right value for each of these edges. Each neuron that connects to another neuron, we have to determine how strong is that connection. And that's the choice we have. It could be that it's a very strong excitatory connection, very strong inhibitory connection. We don't know initially what the right weights are, but what we do is we just feed in data at the bottom, generate output from the model, compare it to what we were trying to predict, and then update all the weights to make the predictions just a tiny bit more accurate. Feed in some new data, get an output, compare it to the truth, update the weights. We go through this kind of rinse and repeat, and eventually these models get really good. And there's an important breakthrough called deep learning. Neural networks have been around and virtually unchanged, little tweaks here and there, but no major conceptual changes since the late 1980s. The big change that started happening in the mid-2000s was, we suddenly had much more powerful computers. And it turns out that deep learning is very well set up. Neural networks are well set up to take advantage of parallel computing. So even when computers aren't getting faster, they're just getting smaller and cheaper, and we can pack many more processing cores on a chip. We could do the computation to propagate many data examples to neural networks in parallel. And so suddenly it became feasible to train much larger neural networks. And on top of that, we had much bigger data sets. And we had bigger data sets because something called the internet happened. And so suddenly you have all these companies that have meticulously organized data arranged in these huge databases. And there's logs of all these different actions. There's, there's billions of photographs on Google image search. There's, all the companies have exact data on all their transactions and who purchased them and what else they purchased. And this stuff is sort of easy to query and build data sets out of. Turns out when you have big data sets, lots of compute, deep learning becomes really effective. So, why is it effective? Well, in the past, what we used to have to do is we feed data into really simple models, but simple models are always bad. The people say like simple models, sometimes are good, but the sort of like dirty truth that the simple models are almost always bad if you just feed in raw data. And the art of using simple models was always to try to engineer features, come up with what's the right way of processing the inputs so that the simple model could then get a good prediction. Deep learning, you could think of as basically, you could think of the very last layer of a neural network as a simple linear model. But the rest of the architecture, what it's doing is basically learning a representation. And so what we used to do is basically have data scientists muck around with the features and try to hand engineer good ways of processing data so that we can get out good predictions. What deep learning does is it discovers good ways to process the data automatically and then outputs a prediction basically at the final, very, very end by applying a linear model on top of the learned representation, and it discovers this all jointly. There's a lot of there's a few different sort of basic ways of using deep learning. One is that you just feed in some input and just try to predict some output. And where a giant data set is given to you, where for every example in the historical data, someone says, here's the input, here's the correct output. Here's the input, here's the target value you're trying to predict. And given all that data, this is called supervision. Someone's told you what the right answer is. You try to fit a model so that it can make, good predictions, hopefully now even on new data that you haven't seen before. There's unsupervised learning, which is kind of a underspecified task where you're just saying, hey, I give you a bunch of data. I don't actually tell you what you're trying to predict. I just ask you to try to make some sense of it. And there's a few different ways of trying to do that, either trying to cluster your data into groups of similar points. But I won't get too into that. It's not related to this talk. And there's something called reinforcement learning. And reinforcement learning is an interesting setup where it's kind of in between unsupervised and supervised in that nobody tells you what the right answer is. What they do instead is someone feeds in the input, you pick an action. So it's usually in the context of some kind of automated system, whether it's a robot that acts in the real world or a game playing agent that plays, for example, a game like chess or Go or a video game. The idea is the model sees some input, it picks an action. Nobody ever says this, no, like you should have picked this other action. No one ever tells it what was the right action. But what happens is that the model eventually gets some signal that says, how well are you doing? So it never says what is the exact right thing you should have done. It just gives you an evaluation, right? It's like kind of like when you get a grade on an essay, right? You're supposed to write an essay on a topic and then you get a grade. And the teacher doesn't come back and say, no, you should have written this other essay. It just says, this is how you're doing. And that's a little bit harder. You have to back out from that. Okay, wait, what did I do wrong? What would have happened if I had done something else? So on the supervised learning front, we've made huge advances. There have been people have come up with all kinds of clever ways of building specialized neural networks for computer vision, for dealing with text and generally sequentially structured data like medical records, text, for translation, for recognizing things like parts of speech and named entities in text, and even for other sequentially arranged data. So in a lot of my work, we've developed methods for dealing with sequential data in the context of things like medical diagnosis, dealing with electronic medical record data. And these methods have sort of gotten more and more advanced just in the form of sort of scaling them up. So today, on the natural language side, you might have seen a lot in the news about things like GPT-3 and DALL-E and these advances from OpenAI and Google. And basically, these guys haven't introduced just about any new ideas. What they're pushing on is, what if we take the stuff that's already working and feed in massive amounts of data and find a way to train models that are 10 or 100 or 1,000 times as big as what people were doing before. And it turns out that, you do get really impressive results when you do that. And so a lot of these models are still trained for various predictive tasks, but, are able to do some really impressive things. A lot of models, what they do is, when I say, on one hand, there's a sense in what we're doing is mere prediction, and that is that we're learning associations. But it's important not to be too dismissive about the power of prediction. Even just pattern recognition, even without actually giving, say, causal insights into the world, there's a lot of things that's not obvious to people at first glance, that they're prediction tasks or that they're purely associative learning tasks that can be expressed that way, and we can apply this machinery to. So one example is, it's sort of obvious that if I feed you an image and I ask you predict, does it depict cancer or no cancer, or is there a face in the image or no face in the image? That's a prediction task. But you could also have a task which is, given a block of text, predict the image that would be the image described by that text. And you could create a corpus where maybe you would have captioned images. You feed in the caption, generate the image. Predicting a photograph it's a weird sort of prediction task, but it's something we do well at. So there's a family of techniques. Maybe the most famous one is a family of techniques loosely based on something called generative adversarial networks, where basically you train one model, gets in some source of random noise or maybe some input that you're conditioning on, and it just outputs an image. Then this image is fed to a different model that tries to predict, is this a real image or a fake image? And when these were first proposed, they got results that looked like this. Then they got results that looked like this. And now they get results that look kind of like this. And this is even old. This is already 4 years old. You've probably seen now that you can also not just generate an image, but generate an image based on a caption. And so this is, you've probably seen all over the news these days, talk about a model from a group called OpenAI, and this is called DALL-E 2. And here you could just type in a description and the model predicts an image. And people are having a field day with this because you could type in some really wacky descriptions and still get out, strikingly interesting and seemingly conforming images. So here someone types teddy bears mixing sparkling chemicals as mad scientists in a steampunk style. And you actually get an image that, it's hard to imagine coming up with a sort of more appropriate image. So, these systems, again, they're just making predictions. They're just doing it based on the data they've seen. But the data they've seen in this case is the entire internet, right? So groups like OpenAI, they've taken sort of a full web crawl or really something really close to that. taking all the images where you have both the image and a corresponding description, which is readily available for many images on the internet, because you have, for example, in browsers, people usually put a description associated with every image. So that way there's something to, for example, people who are blind are able to hear a description of the image, so they are able to track what's going on. So this is a important accessibility feature, but it's also a great source of annotated data to people who work in machine learning. So other examples on prediction include diagnosing retinopathy, detecting skin cancer, and a lot of cases where in a pure predictive setting, when all the sort of basic machine learning assumptions are respected and we assume the world is unchanging and we train on one data set and we evaluate on just a random partition of the data that was held out from the training, we could do sometimes as good or better than humans. For example, as well as human doctors for recognizing skin cancer. So there was a catch in there, though, which was under these idealized conditions when the world is not changing. And so the problem is that the world often is changing. So in summary, the state of the art is we have major advances in pattern recognition. We're able to handle high dimensional data. We're able to handle the kinds of data that are, these raw perceptual signals like images, audio, unstructured text. The bad side is that this technology learns patterns and it makes predictions, but there's a big shortfall from that to, how where we are in terms of our ability to make decisions. And a lot of context, if you look just a little bit deeply, you realize that what people are promising isn't just, hey, I can make really cool predictions. It says, I'm making a stride towards personalized medicine, something like that. And when you look at, for example, the sort of implosion of groups like IBM Watson, which sort of failed to deliver on the promise of, using AI to improve healthcare, you realize that these problems need to be treated with a certain level of seriousness. And so in a lot of our work, we tend to, we are aware of, and my roots are in deep learning research and developing some of this technology. And the power of these tools should not be underestimated for what they are good for. But at the same time, it's important not to be naive about, what do these advances buy you and what do they not buy you? And how do we fill in those gaps? So, the big steps are, how do we get from just wildly, fantastic tools for pattern recognition to being able to provide actionable guidance for companies to make decisions, for doctors to make decisions, for institutions to make better decisions? How do we account for these various, other desiderata that are usually not modeled at all, like various sorts of ethical concerns that arise in application domains that we envisage, using this technology? And also, how do we handle environments that are shifting in all kinds of ways? So, the cartoon picture of what's going on here is that the basic modeling assumption people tend to make is what you do is you sort of assume that, okay, there's some environment characterized by a bunch of data, and we're going to assume that God just, showers data out of the sky, and we put out our bucket and we collect a bunch of data, and we use this data to train a model. And the idea is that, we're going to be able to just go into the future, into some new environment, and it's going to be the same God in the same mood who's going to shower out data that looks exactly the same, statistically indistinguishable from what we've seen before. And so whatever model we trained on the training data, and however well it performed on, say, some holdout partition of the training data, it'll perform more or less exactly as well in the deployment context. And this is the sort of like kumbaya, everything is great world that much of machine learning is operating in. But the real world is, God's a bit more temperamental and, or at least a bit more interesting. And so, we have some data, we collect from some source, some historical data, and then we build some kind of machine learning models and we think we have a good predictor and we go out into the wild. And suddenly, that was last week. That was May, but it's June now, and data looks different and something's changing. And, maybe it's text and people are using new words. Everyone, as I'm getting old, I'm realizing first time in my life, I'm really old enough that some of my students use slang where I just really am like, what the hell are you saying to me? I do not know what the words you are saying mean. Explain it to me. I'm not on TikTok. So that happens in language. It happens in images. You had a system that worked great under some generation of GE MRI machines or something, but now they came out with a new scanner and it has a new sensor, and the images are maybe overall better and sharper, but they look a little bit different. And is the system going to still be accurate, or is it going to be wildly inaccurate? The answer is we don't know. And unfortunately, very often things do break. And this has really serious implications for the feasibility of things like, self-driving cars that, because it's like, how do you evaluate a self-driving car? It looks like it's doing great today, but when the data becomes, 1 year stale, will the system still be doing great? Or what if someone comes up with a new style of paint that has a new kind of sheen on it, and they start painting cars that way, and all of a sudden all the Teslas start killing pedestrians or start rear-ending people or something? So this question of how do you deal with a dynamic environment, how do you build robust and reliable machinery is really crucial. And there have been a lot of demonstrated failures. So one, very famous example is these adversarial examples. You take an image and you alter it by just adding the slightest amount of perturbations to the pixel values. But it's such a small change that a person, right, when you look at the image on the left and the image on the right, not only do you think, oh, they look similar, you actually wouldn't be able to say, my guess no one here would be able to say definitively, are they actually different in any way? The changes are so subtle that we can't even tell the difference. But the image on the left gets classified as a pig by the machine learning model. And the machine learning model, once you've doctored it in this tiny way that's imperceptible to humans, calls it an airliner. So that's one example of these models. They perform well, but you can apply small perturbations. It shouldn't make a difference, but they do. This is also a problem in text. So with my student Danish Pruthi and our good friend Bolan Dingra, who's now a professor at Duke, we wrote a paper. I guess now everyone's a professor. Danish is also going to be a faculty member. We showed that this is a problem even in text, that you can introduce a tiny strategically chosen spelling mistake, and suddenly a model that otherwise got near perfect, 90-something% accuracy is doing worse than random guessing just because you've added these little issues. You have other issues where people create a data set to train a model to demonstrate a capability, but the data set doesn't really correspond to any specific real world deployment setting. And sometimes these models that are trained in these systems actually fail to generalize to real data. And so this is from work with my student Divyansh Kaushik that received the Best Paper Award at a Natural Language Processing Conference in 2018 for demonstrating this. Another problem that emerges is something called feedback loops. And we're studying these more and more. But these are things where, we've been talking so far about a setting where, the world changes in some kind of like passive way. What if there were a small shifts in distribution, but very often it's like the model invalidates itself, even if people aren't trying adversarially to mess it up. A good example is something where basically, you train a predictive model based on what people are clicking on in Netflix. That gives you now a recommender system. The problem is once you deploy that recommender system, you change people's viewing habits. And once you change people's viewing habits, the whole distribution of what people see and what people have clicked on have changed. And now the model is no longer valid. And so now you have to update the model, which makes people change their behavior, which gives you different data, which makes you change the model. And you can have these weird kinds of spiraling effects where, all kinds of strange and possibly undesirable behavior can emerge. So you might think like, well, let's just build a model that doesn't have any of these problems. Let's build the one master machine learning system. And the problem is that that's impossible. It doesn't make sense because there's many different plausible like situations that we, can emerge that are realistic. They're like, they're a good model for one way the world can change. And a different model is a good model for a different way the world can change. Where both are, it's not that there's one that's right. It's that any given environment could be like in this group or could be in that group. And what is the right method to apply is very different for these different settings. So if you don't posit anything about what is it about the world that's stable and what is it about the world that's unstable, sort of all bets are off. So the trick is to figure out, well, how do we figure out specific, well-motivated settings where these problems can be handled? And then how do we help people to, collect the information they need to determine which is the applicable setting in any given scenario and employ the appropriate systems that can be either robust or adaptive and handle that kind of change. So there's a wide landscape of groups and different lines of research trying to handle distribution shift. There's in the middle there's a lot of people in the deep learning world who are very used to this sort of model of let's just tweak the model in a way and see if it's good. And the problem again is that it doesn't really work in this setting because there is no one good model. You have to understand which models should be applied in which environments. There is no model that's going to work in every environment. You need to know something about the nature of the dynamics in order to know which system to apply. And so this is an area more so than prediction where theoretical coherence and like solid foundations are absolutely essential because the sort of train test paradigm falls apart. And then danger is bridging the gap because there's the stuff in the middle of the empirical deep learning approach, which is sort of let's just try stuff. And it kind of, that works for developing predictive models, but it's fallen apart here. So on the one side, we need to develop theoretical foundations and sort of like principled machinery for making these robust algorithms. And on the other side, we have a real world that is, doesn't respect oversimplified assumptions. So any assumption we make, very often it's going to be just a little bit too strong. And so we have to kind of be doing this go-between the real world on the right and the sort of theoretical world to make sure that we're checking in and that we're developing the right sorts of theory and the right sorts of machinery. So I think we're reaching towards the end, but I'll just in a couple minutes kind of summarize some of what my lab's doing to make progress on these problems. Broadly, we've been working with what we call like structured distributional shift problems, things where in some sense, every distribution, or not every, but in some sense, many distribution shift problems are causality problems in disguise. We don't necessarily always call them problems concerning causality, but they really are. They're different from the traditional causal inference problem. Traditionally, causal inference problem, you're saying, I'm going to look at some data and now I want to sort of postulate, I want to extrapolate, like what would happen if I did this versus if I did this? These are two different hypothetical worlds. What if I give everyone treatment A? What if I gave everyone treatment B? These would induce two different distributions. And I want to know, well, which one's better? Which one should I do? With distribution shift, you can think of it more, not that you're the one making the intervention, but more that because the world has changed, something has been intervened on. Some aspect of the underlying data generating process has been perturbed. And so if we say nothing about what has been perturbed, there's no way to deal with the problem. The problem becomes intractable, it becomes underspecified. But if we know something about what can change and what can't change, then we can make progress. So like disease is a good thing. Disease diagnosis, we know something, which is, hey, the prevalence of a virus can change. On the other hand, in the short run, maybe what are the symptoms given that you have the disease don't change so much, right? And so we're able to say, okay, if I'm seeing a bunch of people in the electronic health record system, I want to figure out, what's the likelihood that each person has this disease? Well, that's changing over time as the prevalence is changing. But I'm able to use this knowledge that the prevalence is the driver of the change in order to adapt my model on the fly. Now, I might need to now go a step further and say, okay, but actually, if it's COVID, there's a couple different variants, and the relative proportion of the variance is also changing. And this is the kind of thing that, if we're a little bit more subtle, we can also handle some of these sorts of types of, more refined structures. So overall, we need to say something like, what is it about the world? What is the sort of structure we have? What causes what? What parts of the model can change? What parts of the model can't change? What are the things that we get to observe in each time period? What is our objective? What are we trying to estimate? What is the predictive model, or what is the thing we're trying to quantify? And then which relationships here are estimable? Because if you have like a, giant X-ray images and then you have a disease, well, you can estimate the likelihood of the disease given the image. You can't estimate the likelihood of the image given the disease, because we don't know how to we don't know how to estimate the probability of a million-dimensional object. So within all these constraints, we can set up certain well-motivated problems where there's something we could do. And I'll kind of just blitz through them a little bit, but we've worked on, I could say just at a high level, there's sort of two big challenges in this line of work. One is, how do we make it practical even when our data is super high dimensional? And as I was saying before, there's certain things we can estimate and certain things we can't estimate. And on the other side is, how do we make our assumptions as weak as possible, as mild as possible, so that we're able to and accommodate worlds where maybe the assumptions are mostly right but violated in sort of small ways. So we've come up with this whole technology for how we can leverage. Basically, the one thing we know we're really good at is when the world doesn't change, we're really good at doing classification. We're really good at doing discriminative modeling. And so a big move that we've made is to figure out, how do we leverage our ability to do classification in a problem where there's no distribution shift, to basically turn that into the capability to solve one of these distribution shift problems? How do we formulate the problem in such a way that we can use the classifier that is trained in some appropriately chosen problem where there's no distribution shift as an instrument to now solve the distribution shift problem, where we're able to sort of leverage the structural knowledge that we have? And so we've done this in the case of label shift. So label shift is the case I was describing before, where the prevalence of the different labels can change, but the probability of the manifestations, like the number of cats and the number of dogs can change, but what a dog looks like and what a cat looks like doesn't change. We're able to sort of adapt in these environments. We're able to do this, leverage that technology now to build tools that can detect with very high accuracy when there's been a shift in distribution. We're able to extend this technology to handle the case where a new class arises. And to do that, we had to take a step back and say, well, what if there was, before we can handle many classes that are all changing in prevalence and a new label can show up, we had to step back and say, what if we've only seen one class and a new class shows up? This turns out to be a problem called PU learning that had been addressed, but sort of there weren't practical tools that worked in the deep learning world, and we had to develop them. We then were able to make the leap to this, what we call open set label shift problem, where a new class can arise, and on top of that, all the previously seen classes can shift in relative prevalence to how prevalent they were before. We're able to deal with some problems where even if there's no labels, if we know the label shift assumption holds, we're able to discern, based on the ways that the distribution shifts over time, what are the underlying classes and identify them, and do that even in high dimensional deep learning worlds. This is new work that you might be the first people I've ever seen me mention it in public, but the work that we just submitted for publication. And additional thing that we've been looking at is when the underlying data is relatively stable, the underlying sort of true data, but there's a change in the level of missingness in the data. And this is something that shows up all the time in medicine. So I'll give you a quick example. You go to a big hospital and you look at the health records and you say, what fraction of people in Pennsylvania, in some big hospital system have a COVID vaccine? What fraction of them have the tag, the code in their medical record that says they have a COVID vaccine? And the answer ends up being something like 40-something%. Yeah, that's too low. We already know from the CDC that 80-something% of people are vaccinated. What's going on? Well, what's going on is that a lot of people have a vaccine, but they haven't been to the doctor in a couple of years. So their primary care physician doesn't know they had a vaccine. Or they've been to the doctor, but the doctor didn't ask them, or the doctor asked them, but nobody bothered to enter it into the medical record. So you have this case where things are underreported. And the level of underreporting isn't something like intrinsic to the physical world. It's an artifact of record keeping. So if overnight a hospital were to adopt a new intake form that asked people a bunch of questions, suddenly the level of missingness would change dramatically. And with it, the optimal predictive model for recognizing diagnoses, et cetera, would also change. And so the question is, when the level of missingness changes like this, how can you accommodate that? How can you recognize it and adapt on the fly? And this is another area where it's new work that we're excited about that was also just recently submitted for publication. So I'll end here, but I hope I've communicated something about both how this technology is really exciting, but also something about how it could be really brittle and how sort of fundamental advances are required for us to sort of have a sort of reliable toolkit that allows us to deploy this technology in actual sort of dynamic and changing world without just everything falling apart catastrophically. So yeah, thanks everyone for coming, and thanks John for organizing everything and for being the ringleader here.
Well, Zach, let me ask you one question just to begin our time here. Is we have a lot of business leaders here on the call, and they're thinking about how can I use artificial intelligence, machine learning to make better business decisions. Do you have some applications that are working really well now in the business field? Or do you have some advice for them in how they actively use machine learning and artificial intelligence in their businesses?
I mean, there are so many ways, and I guess I think business is one of these kind of amorphous categories, right? That it's sort of there's so many categories of decisions that a business has to make, whether from hiring to who do I show what ad to inventory decisions about what products should be routed to what facility, and not just sort of at that level, but also how much of each item to order, how much to stock. So I think all of these are areas where companies that are using machine learning in clever and intelligent ways and being smart about anticipating ways technology might break are using it with some tremendous successes. So in the first place, for all the problems that we talk about with recommender systems, like feedback loops, et cetera, those problems are very real and should not be overlooked. And at the same time, there's no denying that, I think compared to sort of the earlier days of e-commerce, the power of recommender systems in increasing business has been absolutely dramatic. I think probably I'm not on the ground on the operations side, but I know people who are in many different companies. And at this point, I think many of the most sophisticated players in terms of companies with large scale fulfillment problems are it's an integral part of what they do at this point, to whether it's demand forecasting or some of these other problems. There's a lot of the I think smartest companies these days are being very sophisticated. I talked about the difference between causal insights and just good prediction. And a lot of the, I think, most sophisticated companies today are, and increasingly getting very serious about how they derive causal insights from the data that they have. And this includes two things. It includes both one, sort of much cleverer use of the observational data that they have, together with the sort of causal machinery, to figure out, the benefits of taking one action versus another, and using just observational data. But on the other side, getting very sophisticated about running experiments. So one thing that's really nice about an experiment is that when you run a well-designed experiment, you can sort of collapse the prediction world and the causal world into one, right? So if I want to figure out, is a treatment helping or is it not? Well, this is difficult because, I look out in the world and I say, oh, people who received this drug tended to die more often. But maybe they died more often because the drug was really powerful and really expensive. So the doctors only gave it to people they thought were already at the highest risk. And there's this background, we call it confounder. And actually, maybe this is by far the best drug, but because it was selectively given to the sickest people, and where sickness was captured in ways that weren't reflected in the data, it had a higher mortality rate, even though the causal effect was actually that it lowered mortality. So, however, if you assign the drug uniformly at random, pick 50% of the people given drug A, 50% of people given drug B. Now there's no background sort of confusion of like something that could have, be the real explanation lurking in the background that influenced who got the drug, because the drugs were assigned by a coin toss. So a lot of companies are very sophisticated about how and where they run experiments. Trying out new features on a subset of users, figuring out what are the right metrics to track, not just looking at the average effect, but even then estimating personalized effects, but based on data that comes from these randomized controlled trials. So I think a combination of pattern recognition and experimentation to get out personalized, but actionable insights is taking off. And I think you'll notice that you see this if you look out there, that there is, of course, still a wild amount of interest in sort of people with deep learning and computer science type skills. But that, it's a much smaller community, set of people, the subset of us who work in causal inference, and that includes not just us, but economists, econometricians, epidemiologists, some people from stats who really focus on these causal estimation and identification problems, are suddenly becoming quite in demand at a lot of the big companies. And so, there's so many different ways that I think machine learning could play a role, whether it's in recommender systems, whether it's in operations.
Great. Thank you. That's a great answer. We're going to just do a rapid fire on a few of these questions we got from our alumni audience. First, will AI and machine learning ever be approximately correct enough for autonomous vehicles?
Ever? So on one hand, I'm like, I tend to be, a bit more on the, there's a part of the community that is completely glassy-eyed and a bit gullible, and I tend to have a bit more of like the skeptical scientific disposition. But that doesn't mean, skeptical means things need to be proven to you, not that you assume that they're wrong or you write them off as impossible. And so will they ever be? I think if we, if we don't manage to like kill ourselves as a species and wipe ourselves off the planet or something like this, I think we'll eventually get there. Yeah, timescale is a much harder thing for me. I'm with any of these things, I'm very reluctant to take a hard stand on anything of like anything that we know is possible, like doesn't violate the laws of physics because we can do it ourselves. I'm very, very skeptical of anyone who purports to just say, oh, that's impossible. But that's very different from taking a stand on when we'll achieve it or how likely it is to happen in our lifetimes.
Okay.
Yeah.
Good. Do any of the ML approaches use Bayesian networks?
Well, Bayesian networks are just a way of factorizing a probability distribution as a graph, where what a Bayesian network says, what the semantics of a Bayesian network are, is that they express a set of conditional independencies. If I draw a Bayesian network that has A, B, and C, where there's an arrow from A into B and B into C, it says that A and C are conditionally independent given B. And there's a language for reading off of a Bayesian network the full set of conditional independencies that they encode. So it's this language of factorizing probability distributions using what we call directed acyclic graphs. The entire sort of modern field of causality relies very heavily on Bayesian networks. Causality, though, isn't just Bayesian networks. It augments the language of Bayesian networks with a causal interpretation. So from a Bayesian network standpoint, A and B with an arrow, or X and Y with an arrow from X to Y, and X and Y with an arrow from Y to X mean the same thing. They just mean I'm not expressing any conditional independencies. But the causal semantics are very different. The causal semantic says intervening on X induces a change in Y if there's an arrow from X to Y. But intervening on Y does not make it so it's augmented with this causal interpretation of the direction of the arrows. And on top of that, a notion of an intervention. An intervention basically says if I ignore however this variable would normally have taken its value, and I basically delete all the incoming arrows to that variable and I hard set it to something else, what would have changed? So Bayesian networks as a sort of underlying set of tools that are now subsumed into a slightly more expressive language of structural causal models are widely used. The entire sort of like modern sort of like the school of causal identification that comes out of Yuta Pearl, which I think is and he's not the only person, but maybe the foremost proponent and a great pioneer and innovator in that area. That entire machinery relies on Bayesian networks under the hood, but it's not just Bayesian networks. There's a little bit more to make them, but basically everything that applies to Bayesian networks also applies to causal DAGs, but causal DAGs extend them.
Great. As explainable machine learning, inexplainable machine learning, what is your opinion of shapely additive explanations? Can you point me in the direction of good explainable techniques? That seems to be a common question among our
audience. Well, I think the problem here, so I'm actually something of an authority here. And the problem here is that there's a lot of people who don't know almost anything about. So usually when you want an explanation, why do you want an explanation, right? You want an explanation because you want to, you want to, very often it's, first of all, it's like, what are you explaining? Are you saying something about the model, or are you saying something about the world? If you're saying something about the world, these methods are absolutely useless. And so even for saying something about a model, it's unclear. Most of these methods, Shapley values, Lime, Deep Shap, GradCam, whatever, most of them, they're at the level of mucking around heuristics. Most people, even the people who propose them, they don't really know what they mean. They have no attached semantics. They're heuristics. Someone says, oh, I generated this prediction and I just want to know, why did I get that prediction? But they don't understand, like, are they saying why, like in the real world, what is the mechanism in the real world such that labels should be applicable given that input? Or are they just saying, which features were important? But when you get to a situation where you say, I have a model that looks at 9 million features, and I want to say, which ones were important for that specific prediction? It doesn't actually have clear semantics. It's not clear what the questions mean. And I think we have this weird area where a lot of people, usually when people talk about explainability or explanations, it's reflecting the fact that there's a real concern. Like, it's not enough to just have a predictive model. There's something that you need to guide a decision, whatever it is to your purpose, that's not just captured in saying, here's an estimated likelihood of some target. The problem is that this set of tools that's emerged, it's mostly come about in this very sloppy ad hoc way of people saying, what if I look at this? Is that an explanation? So there, and part of the problem is that most of the people who look at really more profound questions about causal explanation, for example, have self-selected out of reviewing these papers, have self-selected out of community because it's such a rotten swamp full of some of just the very weakest research. And what ends up happening is that we have bad papers being peer reviewed by only those people who are willing to peer review them, who are the same people who are writing these papers. And then you wind up with a bunch of methods that it's unclear what they're claiming, unclear where, if anywhere, they're applicable. And then people are adopting it anyway. And then, people like me, I wrote the paper in 2016 and saw this all coming. And remarkably, the problem is the one thing you cannot combat with writing is illiteracy. And I think we're in an area where there's just so much interest and so little critical thinking that, there's this whole sort of bag of things that people are calling explanations without anyone using it, anyone proposing it, anyone in that whole conversation stopping for 4 seconds to think what the hell they actually mean. And so the reality is there are some people in causal explanation, people in scientific explanation, philosophers of science who think really serious about what we mean. What does it mean for a model to have explanatory power? And what does it mean to attach an interpretation or semantics to a model? But the sort of broad, explain the black box deep learning world is, I'd say, something that you have to approach with an extremely high level of caution, because most of the research is not fit for human consumption.
Well, Zach, we are so glad that you and our team at Carnegie Mellon University are on this, and we look forward to more insights and perspective. We appreciate the work that you and your PhD students are doing, as well as your colleagues across campus, and grateful that you're also helping teach our students here at the business school how to approach this area and how to apply these in the business world. So thank you so much for your time today. I know we have more questions than we could answer today. We went a little longer, but we knew there was some interest on it. So we will look forward to you coming back another time to update us on this, and when the wall's been painted and everything looks good again. So thank you for taking time out of your very busy and active schedule to be with us today. And we look forward to hearing more from you and your amazing team.
Great. Thanks so much, John. And thanks for all the great questions.
Thank you.